Alrighty, once again, thank you for joining us. I'm Eric with the department. I'm an environmental engineering undergrad here, joined by our wonderful research team and our fantastic technical awareness group. Today we're going to host the first TAG meeting for our new project, which is a multi-objective agent-based modeling and optimization framework for single-stream recycling programs. And here's just a brief overview of what we're going to be covering today. Motivation, what our objectives are, how we plan to go about that. The challenges of single-stream recycling, which are fairly distinct from the challenges we faced in our prior project in integrated solid waste management as a whole. An overview of our proposed framework, feedback from everybody here, and finally a discussion of the benefits of our project. Single-stream recycling is a system in which we collect, transfer, process, and return to market mixed recyclables. Paper, plastic, cardboard, glass, wood, things that can all be recycled on their own. However, the end users do not need to pre-sort. By eliminating the need to pre-sort, it's touted to increase participation rates. Miami-Dade County went to single-stream recycling a few years ago, and we found that is the case in many cases. We also benefit from a simpler collection system. Instead of needing trucks with compartment for glass, compartment for plastic, or maybe even multiple trucks, we can have a single truck for all of our waste. So we have a lot of simplicity at the user side. However, with the simplicity on the user side comes concomitant challenges at the facility side. We need more sophisticated and more costly MRFs, because very simply we need to be able to sort the materials. We can't just have papers here. We need all of the equipment to sort who is who. And we need to maintain a very high quality product to return to manufacturing. Contamination is a big problem at these facilities, and it further drives up the cost, drives up the complexity. So, we're looking at the system both from a high-level view and a low-level view, and we've identified three major components. First, the collection and transfer system, which brings the commingled mixed recyclables from the generation point to a processing facility. Then we have the MRF. The MRF converts these mixed, dirty materials into a clean, standardized product that can be returned to industry. And finally, we have the economic and regulatory environment, which, as we all know, plays a massive role in recycling and what is certified recycling and uncertified recycling. Multi-stream is the more traditional recycling system. It's been out since the 70s and 80s. We have multiple separate containers at the generation units. Generation units pre-sort. We have a separated collection system. A MRF, return it to market. Same end goal. The advantages? Simpler, less costly facilities, because we don't need a sort. Fairly straightforward from a mechanical perspective. And we also are more guaranteed a high quality output material, because we have less contamination to start with. However, the disadvantages are our participation rates are lower, and our collection system is more complicated and thus more costly. If we have a multi-compartment truck, one for paper and one for glass hypothetically, and one compartment becomes full but the other is not, that truck still needs to return to depot, which means we're driving the truck partially empty. As we look at this system, we've identified a series of challenges. And SSR is interesting because it faces all of the same challenges that face integrated solid waste management as a whole, and then some. We're starting off with uncertainties. Uncertainties are present in solid waste management, present in SSR. We don't know what will be the availability of our capacity. We don't know the day-to-day generation rates. However, for solid waste management, the waste composition is not as important to us. It goes to landfill, it goes to waste to energy, gasification in 20 years from now. It really doesn't matter if we landfill glass or landfill paper. For single-stream recycling, the waste composition is vitally important. Because if my single-stream MRF can only accept X amount of metals, and my composition changes all of a sudden for some reason, that's a very, very significant impact that's going to bring down system performance. And we also have the same system, global level, generation rate, holidays, social impacts, all of these things. We have many stakeholders. The same exact stakeholders who we saw in integrated solid waste management. Regulatory, governmental, we have private contractors, we have public utilities, we have social concerns, traffic, all of these things apply. Many interdependencies. This is new to single-stream recycling compared to solid waste management. In our prior project, we looked at solid waste management after collection. So we didn't need to worry about road network, traffic, things like this, to as big an extent. SSR, on the other hand, is intimately dependent on the road network, because these are the linkages between our generation units at each distinct service location and the facilities. So we need to have a much better command of the road network and much more detailed use of it in our modeling than we had before. Also, we need to know the nature of the generation units, because a ton of garbage made at a residential unit and a ton of garbage made at a commercial or an office building are going to have very different compositions. The total inventory of the materials dictates how we design our facilities. So these are all things that we need to keep track of, and all things that are ultimately uncertain. And finally, we have conflicting objectives. The first two, classic dichotomy. We want to minimize cost and we want to maximize recycling. No news there. However, something we're also looking at is job creation. Our prior work, as I've mentioned before, deals with solid waste management. Title is a simulation-based optimization framework for solid waste management and recycling. We developed a novel hybrid agent discrete tool, which allowed us to very, very accurately model both the interaction between facilities and their internal operations. The agent-based model could very, very accurately say so many tons of garbage are being transferred from point A to point B, what time they're going at, how much it's going to cost. Very accurate because it's an agent-based model. While the discrete component allows us to very accurately model unit operations. 1 garbage truck, 2 garbage trucks. It's very, very difficult to make 1.6 garbage trucks. So we retain that discrete capability. And we're going to be carrying over a lot of the facility data that we collected. Even though we didn't touch SSR there, we still need to know about the landfills, waste-to-energies, transfer stations, because every ton that we address in a new SSR system is 1 ton less that's going to landfill, that's going to waste-to-energy. And we want to be able to model and show you the impact of that on the existing facilities. So here we have an overview of our proposed framework. We started out with our objective: to develop a tool to simulate and optimize SSR systems throughout the state of Florida. We're also going to be comparing them with multi-stream. For some regions, multi-stream may still be better, may be more economically viable, may result in greater diversion, greater quality. We're going to do that comparison. We have focus areas. We have 4 of them. First, operational performance. Capacity. You can't put 5 pounds of stuff in a 3-pound bag. It doesn't work, no matter how nicely you ask. So we're going to be following that at all of the nodes, at all of the facilities. Economic performance. Costs, revenues. Once again, we need to maintain a financially feasible system. Environmental performance. We're looking at the recycling rate, which is a fairly common metric. And we're also looking at greenhouse gas emissions. Because a lot of our disposal facilities, our landfills, obviously, you can smell them when you drive by them, producing greenhouse gases, and waste to energy. You have a fire, you're making carbon dioxide. However, by sending things to recycling, we may be reducing that, but we also have the greenhouse gases from trucking them to the recycling plant, from the recycling plant consumes some electricity, some steam in some places. So we're going to be doing a life cycle analysis on our greenhouse gas impact. And finally, we're looking at the collection system, the conditions of the road network, which are going to be so vital to determining the performance of our overall system. Thus, we've developed a framework of 3 components. First, a structured database, then a simulation module, and finally, a fleet utilities optimization module. They're not as bad as they sound, trust me. Here we have a graphical overview. We start off with the structured database. The structured database is the most heterogeneous component here because it needs to store such a wide variety of data. We need data on the facilities, processing, treatment, landfills. We need to know their location, their hours, their capacity, data which we're using from our previous project. We need to know about the generation units. Florida has a lot of them, over 10 million. We need to know their location, their type. We can calculate their waste generation and composition. We need to know about the economic relationships, which are very important to determining whether or not our proposed solution is fiscally viable. We need to know about the road network. The state of Florida has a lot of roads. We need to store them in a standardized manner so that somebody 10 years from now can open up our model who wasn't at this meeting and change the data to reflect current conditions. And finally, the regulatory environment. FDEP is very active. Air quality, runoff, leachate, there are a lot of things that we need to follow. This database stores data in a human-readable format for ease of update. We have a graphical user interface, and it will be very simple for anybody to modify the data and thus modify the system under review. This human-readable data is fed into the simulation module. The simulation module carries a few important tasks. It begins by showing a form asking the user to define a study region, one or more counties. Once we have that study region, it parses through all of the data in the database and determines which facilities, which generation units, which roads are relevant to that study region. It identifies them. It then looks for the uncertainties in that region. Our generation, our composition, our facility availability. It quantifies those. Quantifying the uncertainties is crucial to accurately modeling them because our computer requires numbers. We can't tell it depending on how such and such feels, so we need to quantify it. We take all this data, we carry out a parametrization. Parametrization is a computer process. We convert human-readable data to machine-readable data. That gets flung into the Fleet Utilities Optimization module. The little picture on the left, that's an agent-based network. And you can see the linkages between all of the different agents. Those linkages allow them to transfer material, transfer funds, all of these things. They also get to talk to each other.
Those arcs that you see between the agents, one arc, the interesting thing is it can be one number, it can be one distribution, or it can be another simulation itself. That arc itself can be a simulation itself. It's simulating, let's say, the waste that I'm generating here and sending it over to the MRF. So that arc itself can be actually another model within itself. So we cannot show it over here, but it can show that much of the detail. It depends on how much aggregation we do and how much detail we do.
And here we first build the model based on a series of constructors. By using constructors, the model always reflects the latest database. Thus, we've built in generality. This could be applied to a different geographic region, different set of conditions by changing the human-readable database, which will then change the parametrized data, which is compiled on the fly. Therefore, we have a general model instead of a case-specific model. We do a candidate generation algorithm. We start out looking at the current system, run the model for a predefined study period, look at its performance using a performance analysis tool, that little graph on the right. It looks at economic, environmental, operational, job creation performance. Very holistic review. We then have a meta-heuristic optimization tool, which modifies the operating decisions, the distribution of facilities, the number of facilities, any variable which the user wants to edit. Then runs the model again, does a performance analysis on the new candidate, compares the two. If the new candidate is better, based on an arbitrary objective function, then the optimization continues in that direction. If the new candidate is not feasible or not as good, the optimization algorithm carries out in a different direction. Thus, we very efficiently search for the most optimum set of decisions to maximize the performance of the system. And once again, that's also linked to the database. If we need something mid-model, that linkage is always there. We need a couple tools to carry this out. First, we need an Integrated Geographic Information System, or GIS. This stores all of the georelational data in the system. What's important is that it's a standardized format. It's the data format used by the United States Census Bureau, the Florida Georelational Database, and all of these things. And we carry out network analysis and spatial analysis algorithms. They allow us to provide the model with routing conditions at initialization. Because that routing, the map functionality, is not something we have in the agent discrete model. We use the GIS. We then identify our most optimum solution. It goes to the real system and we complete a feedback loop. we can continuously tune our model based on the real-world performance as opposed to our model performance to make the most accurate tool possible. Structured database, very important, very vast component, stores parameters of all of the 302 FDEP licensed facilities currently operated in the state. This is data we pulled from the previous project. We didn't change much there. The generation unit inventory. The state of Florida has over 10 million generation units. We obtained data from the Florida Department of Revenue with the location and characteristics of these generation units. And we have them in the integrated GIS. So instead of simply being able to say, the city of Coral Gables is X number of inhabitants, we know the exact latitude and longitude of each one. We know what road they're closest to, so we could route a garbage truck to it precisely as it's routed in the real world. In addition to the economic data, the operational data, we have a massive, massive volume of georelational data, which we need to be able to handle. The state of Florida has 840,000 distinct roads. Put simply, if you wanted to drive on a different one every single day, you would need to live to be 2,300 years old to see all of them. So we needed a very effective way of organizing all this information. In addition, we have well over 10 million generation units. Every house, every commercial site. Basically, if it has a post office box or a mailbox, it's a generation unit. We actually obtained this from the Department of Revenue. Everybody who pays property taxes gets to be a generation unit. We also need to provide routing. It's not efficient for us to manually compute 840,000 roads and then try to optimize that. So we need a spatial and network analyst tool to do so. So we used a variety of data sources, the Census Bureau, the Florida Georelational Database, the Florida Department of Revenue, and the FDEP. And here's what we got. We have a few images. This is our most aggregate view. This is the entire state. We divvied the state into 6 regions based on the FDEP reporting regions. So we have complete parity between our information and their documents. Alrighty, and here you see the processing facilities dispersed fairly much throughout the county. This figure doesn't show the relative capacity because we have a very wide variance of processing facility capacities. We have some very large waste to energies out in the swamp, Everglades, thousands of tons per day capacity. And we have transfer stations with 10 or 11 tons per day of capacity. We have that data, it's just not in this figure. Moving to a more detailed view.
Yeah.
This is give or take a 1 square mile section of a neighborhood. The green dots are residential service locations. The yellow-orange dots are commercial sites. And here you see we have a laser pointer. We have 2 multifamily units. This is a suburban neighborhood in Hillsborough County. Here we can see we have residential subdivisions. Here we have perhaps a shopping area, something like this. And this is based on the real system. This is not
And this
hocus.
is more like what we're going to be dealing with for the next case of the project. That snapshot. Yeah.
This is all based on the real road network. We know location, intersections, speed limits, all sorts of things. We have very, very highly detailed view. Moving right along, we have more views of the road networks. We actually know the name of the road. We were able to separate the freeways from the local roads because the model does not know if the generation unit has an address on a side street next to I-95 or I-95. And it would not do us very much good to collect garbage from the side of Interstate 95. So here we have everything nice and delineated. We have the ability to route garbage trucks on the freeways to send to the processing facilities, but we're going to be collecting on the secondary or tertiary roads. Once we have all of this data, the economic data, the operational data, the georelational data, we feed it into the simulation module. Simulation module converts all of that beautiful human-readable data, which can be easily edited, which is based on the real system, into machine-readable data, which our model will be able to use. It provides a graphical user interface that allows the users to define the study region and options, such as transfer utilization, hours, things like this. And most importantly, it identifies the uncertainties in the given study region, both in terms of our facilities, availability, and in terms of our generation, the day-to-day generation rate, and the day-to-day composition. it would cause quite some problems if, for instance, in Hillsborough County, which has a large metal demand, if that MRF was not designed for that metal-heavy flow, it would cause operational issues. So this is all data that we need to be aware of, and uncertainties and day-to-day variability, which we need to model. This is the breakpoint between this TAG meeting, this reporting period, and our next reporting period, where we start actually developing, compiling, coding the model. So we're going to talk about our dissemination activities. We have 2 abstracts under review, one with the Industrial and Systems Engineering Research Conference, ISERC, hosted by the Institute of Industrial Engineers, and another at the SWANA Conference in January. We've developed a very strong relationship with industry, which has been a tremendous asset throughout the last project, this project. We've worked with Miami-Dade County, Waste Management. We've had multiple site visits. It's been a tremendous asset to helping us learn the needs of the real system, the way the real system operates, the way the real system needs to see data. So that's been a very strong asset, both in terms of what we see and the discussions that we've had. The summary of benefits. Like the last project, this project expands on the literature and existing solutions and existing frameworks and what we can provide. The database. Our last phase, we developed the first unified database of all of the processing and treatment facilities. Now we're developing the first unified database of all of the processing and treatment facilities, all of the millions of generation units in terms of their location, their classification, single family, multifamily, and all of these things. And all of the roads in a single database tool, which could be distributed, very easy to manage. Modeling scope. Our last project, we were the first to carry out a life cycle analysis post-collection from economic, environmental, and operational perspectives. Here, we're continuing that holistic perspective. Instead of having one model for cost, one model for operations, we have all of that together. Only we're expanding it to both collection and post-collection. Therefore, we're presenting the first life cycle analysis for the entire solid waste management cycle from all of these perspectives. Geographic scope. Once again, we're going to be covering the entire state of Florida. More importantly, through generality, we have a general solution which could be applicable to any region, simply based on the human readable data and the GIS data which is provided by the user. And ease of update. You don't need to be a programmer to update the human readable database. Through the use of SQL, graphical user interface, it could be very easy for a user to modify the model to perhaps review a proposal or any number of other things. Thus, the proposed tool, in order to meet our objective functions, provides regional and county level planning, provides a uniform environment in which we can look at various alternatives under the same set of conditions. Instead of whoever designed alternative A having a model, alternative B having a different model, we have one tool that can look at all of the alternatives. We have a means of simulating the impact of a capital project, a roadway project, a change in generation units, perhaps building a new residential subdivision, on the dynamics of the entire system. Thus, for instance, building a new MRF. Instead of just knowing how much material that MRF can take, we can model what the impact of that new MRF will be on the neighboring waste to energies. Perhaps they will get less material. Perhaps the material they get will have less paper and more magnesium. Any number of things. We have that level of detail. And we have that at all of the different levels. We could simulate the impact of a new facility on the generation units. Will their collection times be changed because of the location of the facility? These are all different scenarios we can present. And because we can present all of these scenarios, we have a means of achieving the 75% recycling goal in the most cost-effective manner possible.